So, not to repeat the long title, in other words, this work is about developing a system that would use off-the-shelf programmable microcontrollers such as BBC microbit, because usage of microcontrollers allows for collection of objective data and real-time feedback, which could be helpful for skaters to train execution of basic exercises where mutual position, orientation, and three-dimensional acceleration of skates are very important for correct memorization and further execution. Research question is to determine suitability of radio link, sensor data acquisition, real-time system performance characteristics for the conditions of ice and inline skating physical exercises execution. Relevance of the study is more evident in our online and hybrid reality where in-person training is hardly available, yet correct repetition of exercises at first steps of training are still as important. In response, microcontroller-based system of correct repetition of exercises at first steps of training are still as important. In response, microcontroller-based system with real-time kinetic assessment does not require physical presence of specialists, and apart from recent events of typicality of this work, typicality is related to growing popularity of Internet of Things and constant search for applications, integrations of Internet of Things for solving real-world problems like the one given as an example. During the main research was confirmed the possibility to use radio channel devices paired with real-time visual Python 3D visualization on a computer by a radio to serial bridge link. In exploration of performance limits of the proposed system, sensor reading and channel transmission performance tests were made and bottlenecks identified. And finally, actual data reading tests were conducted with basic inline exercises that are common for both inline and ice skating. Now let's dive into physical details of the prototype. 2 microbits running on compact 3-volt AAA batteries, all rigidly attached to a pair of inline skates from the outer side in a way such that positive direction of y-axis of accelerometer corresponds to increase in rotational potential energy. It means it's oriented directly away from the center of Earth and both feet are on the flat surface. The third microbit is connected to a computer by a USB cable and is supplied with power from the computer. As an attaching material of microbits to skates was used hot glue in the version on the photo. Another variant would be to use nylon buckles. On the next level, there is logical organization. Firstly, the microbits measure the acceleration of each skate with their embedded sensors, and then communicate the data as a string of text using inbuilt radio on a 2.4 GHz frequency, which is the same as Bluetooth operating frequencies, except that direct microbit-to-microbit radio communication has subtle differences in protocols and has better performance in certain tasks. The microbit connected to a computer receives data from both microbits and outputs it in the serial port of a computer. It also acts as a sensor for a computer for when to switch phases of the running program. And lastly, feedback of choice. To bring the desired system to life, I use multiple software and solutions. Microcontrollers operate on machine code, and for microbits, a hexadecimal source file is needed, and is made from Python code using an official editor. In the background, you can see an actual Python code example for data collecting microbits. As Python is almost pseudocode, you might understand the content without special computer science knowledge. There's also a possibility to use block codes because microbit was purposely designed for educational use. Every run of the program that is launched from the computer begins by calibration, say by pressing a button on the controlling microbit, the one that's connected to a computer, switch to active data collection, and later feedback in form of a graph or a real-time visualization. Another useful tool is a serial monitor of our Arduino integrated development environment that allows to see the serial, like what is outputted by a microbit directly without other programs. Every technology is faced with limitations, usually concerning speed, precision, and range. The conducted tests for different parts of the system showed sufficient results as delay less than 50-70 milliseconds is subjectively unrecognizable. The range of stable communication in different conditions, where it's like no obstacles, non-conducting obstacles, and conducting obstacles, is varying with a result of most effective range up to 15-25 meters without major obstacles, as for example, buildings. The acquired results align with previous research, as microbit operates on the same frequencies as Bluetooth devices, and I could take data from Bluetooth range. In general, signal attenuation depends on air temperature and humidity, as well as destructive interference from reflections, which are not very well controllable. Another delay source, which unfortunately I may not quantitatively measure with chosen technological stack, might come from the accelerometer itself, and it comes from the sensor's internal structure. It is a capacitor, and its relaxation time in default operating mode slows down the measurement rate. However, with another programming language, it is possible to configure the settings of the accelerometer, which provides fields for further development and research. To test the system, I chose a number of basic exercises which are present in both ice and inline skating. This is one of the graphs of one typical exercise, a forward swizzle. It is also called a lantern or a lemon because of its distinct rounded shape. On the plot, you see 3 graphs of corresponding to one dimension. On the x-axis is a number of measurements. This graph was taken at a rate of 100 measurements per second. So it means between every 100 measurements, there is 1 second that passed. On the y-axis is acceleration in milli-g, unusual measurement, but this is 1/1000th of acceleration of free fall at Earth. As I conducted experiments on various terrain, I established that rough terrain is unfavorable because of how sensitive the device is. The small rocks in asphalt and bricks provide constant and chaotic up and down accelerations, as well as vibrations, so it is best advised to deploy either on smooth terrain like gym flooring or ice. In the conclusion, according to bottleneck tests, the radio bridge link with 3D monitor visualization is faster than accelerometer's capacitor relaxation time. Performance tests have showed that in conditions with possible signal attenuation and destructive interference, effective distance of 25 meters is suited for selected activity scope, and proposed reading and data reading and analysis is applicable for training of basic skating exercises. Here's my sources. I took the works that covered fields that are not available to me, like wave attenuation and Bluetooth range. And thank you for your attention. Now I may like to speak a little bit about how I came to this idea and the possible future applications.
Well, thank you, Olita. Yep. Sorry for interrupting.
Yes, of course.
Yeah. Thank you for this presentation. It's very interesting, actually, very unique, I would say. So literally very outstanding one. Thank you for that. And I think Miroslava Charnova is ready to open the discussion session. Yeah. Miroslava, you need to unmute yourself. Yeah, thank you.
Thank you. So thank you very much for presentation, very interesting, and as it was said, it's very unusual in this session because it's more technological, and it is not research. In fact, it is in fact the model which can be used to analyze inline skating, yeah, as I understand. The system, you very described how it works, how the model works, and you also brought some data, and we could imagine how it works and which data we can collect. It seems relatively easy from technological point of view, but in fact it's a very complicated system. I thank you for good idea how to apply microbits for such exercise. And I would like to ask you to whom this model could be available. Is it only for research to analyze the movement, to connect how to get data about movement and how to analyze this data, or if it's also available for example, teachers and to help them, for example, to improve some sport activities with their students. And what's your next plan also? It's my question. Thank you very much.
I'll start from the beginning. As the technological stack you observed correctly, is not very complicated and is absolutely available for all levels of understanding. It might be very useful to ice skaters, just as novice, and because repetition at first steps is very, very important. It might also, as it does not require physical presence of a trainer, and because of real-time communication, a trainer might be sitting at home and watching how the student is performing a task and might objectively understand, is this angle of degree correct or not, because computers do not allow for subjectivity. With further development, it might be also useful for professionals, where subtle details like pre-turn and jumps is crucial, and in judging, it should be penalized. So extra objectivity might reduce scandals that are more and more common now in professional sports. As a future study, I would like to maybe introduce artificial intelligence that could correct on the run, because as the patterns are easily distinguishable even for non-professionals, I think it is a task suited for artificial intelligence to correct and improve self-learning.
Thank you very much. And can I ask, what was the motivation to do such a very interesting model? It's that you are inline skater, or if you are a programmer and you wanted to see how apply these technologies, microbits and programming in Python or other in this model?
I used to be a figure skater, like this beautiful on ice. And also the idea started as because of a lockdown, availability of person training is absolutely diminished, and a system that could help me self-train is something that interests me a lot, because I always find myself in the process of self-education, and I would like to share this possibility with other people.
And I would like also appreciate that you presented some limits or problems which or errors or mistakes which are more technological, and I thank you very much. Thank you very much. You did a wonderful work, and I hope that another sports will also have such support to be modeled by such simple system, because everything is available. Microbits are around, you can buy it very easily, and Python is free. So thank you very much. Thank you.
Thank you, Dr. Chernysheva, for your feedback, and thank you, Olita, for your answers as well. I think that Ms. Fleur had a question for you, if I'm right.
I had a question, but Olita did answer it. I was going to ask your motivation and the future studies, and you have covered that. And yes, I want to emphasize again how impressive that was, and how democratic. Again, emphasizing how you are using tools that are available for all. Thank you so much, Olita.